Day 68, page 272, problem 57, rotational mechanics. It's a takeoff of problem 56, except for we have friction in our rotating cylinder with the little monkey dropping, the 1 kilogram monkey. So here once again we have our cylinder with the thread attached. It starts off the same way. We look at our background information. The cylinder has a rotational inertia of 1/2 mr squared. Relationship between linear acceleration, rotational acceleration, A equals R alpha, or if I just rearrange that, this is the same equation, alpha equals A over R, which I'll use in a little bit here. So we apply basically Newton's second law to both objects. The monkey, F net equals ma, and it's the big force, 9.8, downward force minus the tension force equals the mass times the acceleration. I'm going to plug in there and simplify that a little bit. I'm plugging in a little bit earlier this time than I did in problem 56. The mass of the monkey is 1 kilogram, so we have 9.8 minus T equals 1 kilogram times A, being consistent with all our units. There's just going to be a lot of algebra once we get going here, because the basic principle is F net equals ma for the monkey, and torque net equals I alpha for the cylinder. Except for we have an extra torque that's resisting now the acceleration of the cylinder. This is the torque that's trying to make the cylinder accelerate. This is the torque that's keeping it from accelerating any faster. That's given in the problem, 0.06 Newton meters. The units are good once again, so we can just use that number. So it's the forward rotation or clockwise rotational acceleration minus the counterclockwise resisting torque. Gives you net torque and equals, and I plugged in for the rotational inertia 1/2 mr squared times alpha. And I just plugged in a bunch of the numbers here now that are given are 1.1 meters. Plugged that in for R sub 1. Plugged in the mass and the radius for mr squared for the cylinder. And the rest is, well, you could say the rest is history. Well, actually, the rest is algebra here. Just keep plugging things in. I simplified a little bit in this step. Oh, and I plugged in way up from the top up here. You can see this A over R. Bring this all the way down and plug that in for alpha. And that gives you then A over R, where R is 0.1 meters. And then I'm taking this expression for A, 9.8 minus T, that we got from the monkey, plugging it in for A, using distributive property to come up with this expression, and then just solving for T. T is a little bit stronger than it was in the last problem. The acceleration is going to be a little bit less. We could figure out what the acceleration is by just plugging that in one of the top equations, but that's the tension in the cord. So there'll be less acceleration if you plug that T in, say, well, plug it in right here. I guess the linear acceleration will just be 1.5 meters per second squared as opposed to 1.6 meters per second squared like it was in problem 6. Slightly less here, as you would expect, because there's some resistance, some friction that's keeping it from accelerating as fast as you would expect it to in the previous problem without the friction.